Wait, I thought nothing could travel faster than light. Yet astronomers have measured galaxies moving away from us at 3, 5, even 10 times the speed of light. Is Einstein wrong? Are aliens involved? Or is something even stranger happening in our universe? You've probably heard it 1,000 times. Nothing can travel faster than light. It's the cosmic speed limit, hardwired into the laws of physics. Einstein's theories, which have passed every test we've thrown at them for over a century, tell us it's impossible to accelerate any object with mass to light speed, let alone beyond it. Yet, when astronomers look at distant galaxies, they regularly measure them traveling away from us at velocities far beyond this supposed universal speed limit. Some are moving at millions of miles per second. So, what's going on? In the 1920s, astronomer Edwin Hubble made one of the most important discoveries in the history of astronomy. By carefully measuring the light from distant galaxies, he noticed something strange. Almost all galaxies appeared to be moving away from us. He could tell this by looking at their redshift. Just like the sound of a siren drops in pitch as it moves away from you, a phenomenon known as the Doppler effect, light from receding galaxies shifts towards the red end of the spectrum, a process known as cosmological redshift. The greater the redshift, the faster the galaxy is moving away. But here's where it gets really interesting. Hubble discovered a pattern. The farther away a galaxy is from us, the faster it appears to be moving away. A galaxy twice as far away moves away twice as fast. 3 times as far, 3 times as fast, and so on. At first, this made it look like we were at the center of some cosmic explosion, with everything running away from us. But there was a problem with that idea. It would make us special, at the center of the universe. The more elegant explanation, which has been confirmed by nearly a century of observations, is that space itself is expanding everywhere. If we apply Hubble's relationship to extremely distant galaxies, those billions of light years away, the math tells us they should be moving away from us faster than the speed of light. But how can this be true if nothing can travel faster than light? The answer lies in understanding the difference between moving through space and the expansion of space itself. Imagine dough rising in an oven. The dough represents space, and galaxies are like raisins embedded within. As the dough expands, each raisin moves away from the others, not because the raisins themselves move, but because the dough they're sitting in is swelling and stretching. The farther apart 2 galaxies are, the faster they drift away from each other. Scientists call this phenomenon Hubble's law, and it's our strongest clue that the universe itself is constantly expanding. So, galaxies aren't racing through space faster than light. Instead, the space itself expands between them. Einstein's speed limit only applies to movement through space, not to the expansion of space itself. Near us, in our local group of galaxies, the expansion of space is so minimal that gravity easily overcomes it, keeping galaxies bound together. But far away, beyond the observable universe, what we call the Hubble radius, space expands so rapidly that galaxies appear to recede faster than light. And we can observe galaxies much farther away than this, some over 46 billion light-years away in what we call the co-moving distance, appearing to move at several times the speed of light. But if these galaxies are now moving away faster than the speed of light, how can we possibly see them? Shouldn't their light be unable to reach us? The key insight is this. The speed of these galaxies today doesn't tell us whether their light can reach us. What matters is the integrated effect of expansion throughout the light's journey. When a photon of light leaves a distant galaxy, it's indeed moving toward us at the speed of light through its local space. But it's like a swimmer trying to swim to shore while the current pushes them back. Space is expanding as the light travels. The light we see from these ultra-distant galaxies was emitted billions of years ago, when the galaxies were much closer to us. Back then, they weren't moving away faster than light, so the light could begin its journey toward us. As the universe continued to expand, these galaxies accelerated away from us, eventually exceeding the speed of light. But their light was already on its way, steadily making progress through space despite the expansion. This creates a fundamental distinction between our observable universe, the region from which light has had time to reach us since the Big Bang, and the entire universe, which may be vastly larger, possibly even infinite. There is, however, a real cosmic event horizon, a distance beyond which light emitted today will never reach us, no matter how long we wait, because the expansion of space between us is accelerating too rapidly. As the universe's expansion continues to accelerate, galaxies that are currently visible to us will eventually cross this boundary. Their light redshifted into invisibility as they permanently disappear from our observable universe. Let's look at a concrete example, one of the most distant galaxies ever observed, to see these principles in action. This faint red smudge might not look impressive, but it's one of the most distant objects humans have ever observed. Meet GN-Z11, a galaxy so far away that we're seeing it as it existed just 400 million years after the Big Bang, when the universe was only 3% of its current age. GN-Z11 has a redshift of 11.1, meaning the wavelengths of light from this galaxy have been stretched by a factor of 12.1 due to cosmic expansion. Light that left this galaxy in the ultraviolet spectrum reaches us in the infrared, stretched to wavelengths more than 10 times longer. Based on our current cosmological models, GN-Z11 is now about 32 billion light-years away from us, and it's currently receding from us at a rate of around 3.3 times the speed of light. But remember, the light we're seeing left this galaxy 13.4 billion years ago, when it was much closer to us. This light has been traveling through expanding space ever since, slowly making its way to our telescopes. Galaxies even more distant than GN-Z11 may lie beyond our observable universe. Their light, no matter when it was emitted, will never reach us because of the ongoing expansion of space. So what would happen if we tried to actually travel to one of these faster-than-light galaxies? Imagine we've developed incredible technology that lets us travel at 99.9% the speed of light, right at the edge of what physics allows. We point our ship toward one of these distant galaxies that's currently moving away faster than light, and we take off. As we speed through space at near light speed, space itself continues to expand around us. For galaxies within the Hubble radius, those moving away slower than light speed, we'd eventually catch up, although it might take billions of years. But what about galaxies beyond the cosmic horizon, currently moving away faster than light? The disturbing answer is that we would never reach them, no matter how long we traveled, because they're now receding too fast. Even worse, as the universe's expansion accelerates due to dark energy, more and more galaxies cross this boundary every day, permanently passing beyond our cosmic horizon into regions we'll never be able to reach. So, do galaxies really move faster than light? The answer is both yes and no. They don't move through space faster than light. That would indeed violate Einstein's theories. But they can appear to recede faster than light when carried by the expansion of space itself. This discovery of cosmic expansion revolutionized our understanding of the universe. It led directly to the Big Bang theory, the idea that our universe expanded from an incredibly hot, dense state about 13.8 billion years ago. The discovery in the late 1990s that this expansion is accelerating, driven by a mysterious force we call dark energy, earned the 2011 Nobel Prize in Physics. These faster-than-light galaxies aren't breaking physics, they're teaching us about the true nature of our expanding universe. As the universe continues to expand and accelerate, more galaxies will cross beyond our cosmic horizon. In the very distant future, civilizations might look out into space and see only their local group of gravitationally bound galaxies, with everything else having disappeared beyond the cosmic horizon. These apparent faster-than-light speeds remind us that the universe is stranger and more fascinating than our intuition suggests. They show us that space itself is dynamic, not a static stage where cosmic drama unfolds, but an active participant in the evolution of our universe. If you enjoyed this journey to the edge of cosmology, hit the like button and subscribe for more videos that explore the deepest mysteries of our universe. And let me know in the comments, which aspect of cosmic expansion blew your mind the most? Don't forget to watch the video on the right and subscribe. Thanks for being part of Cosmoknowledge.